It's 3 o'clock, so I would like to, it is my pleasure, as usual, to welcome Professor Andy Cooksy, who is, well, actually a professor in the chemistry and biochemistry department at San Diego State, interim chair now, associate director of the Computational Science Research Center, and he's gonna tell us how to fill in the gaps in organometallic experiments using the computer or using computational chemistry. Andy.
Thank you, Jose. So, oops, let's see. The host has disabled participant screen sharing. Jose, can you let me share the screen?
Oh, I was supposed to make you, or I thought that Parisa had done it, but I guess, so you're supposed to be co-host.
I can describe what's going on.
Yeah. No, I'm not gonna get off that easy.
Oh, I think I can. Let me see if I can do this properly. Let's see, how's that?
Yep.
Okay, great. So thank you very much. I'm particularly grateful to Jose because both of us have had our offices flooded recently in the GMCS building, and this is a nice way to think about something else. The thing I'm going to tell you about today, as the title suggests, is using computational chemistry, not actually the way that we often want to use it. When I got started doing computational chemistry, I was thinking that the main thing we would use it for is predicting experimental results. But in fact, what we've been doing most of the time with it is filling in the parts of the picture of what's going on that the experiments just can't get to. So we're actually spending a lot of time on systems that have already been experimentally studied, but where there are important questions still remaining to be answered. Now, more in general, what we do some laser spectroscopy, so we do some experiments ourselves. We do calculations on small molecules, which we can then throw pretty accurate quantum mechanical methods at in order to predict their properties. We did some code development some time ago to solve the vibrational Schrodinger equation to predict vibrational spectra for some of these molecules that we're really interested in. But what I'm going to tell you about today is where actually right now we're doing the bulk of our work, which is in collaboration with experimentalists. And kind of by accident, we happened into this field of organometallic chemistry, where people are combining metals, usually transition metals, with organic ligands to make compounds that have interesting properties, either in terms of catalysis or in terms of electronics and optical properties. And we're trying to support the experimental work, again, by kind of filling in the gaps where the experiments don't actually give us a lot of information. Really briefly, just to give you kind of a run through of the kind of computational chemistry I'm talking about, what we do is called electronic structure calculations. And the point of an electronic structure calculation is to look at the distribution of the nuclei and solve based on that where the electrons are. So it ends up being a problem in the electronic distribution. The nuclei are generally treated as fixed while the distribution of the electrons is solved. From the standard calculations, we can get the geometry of the molecule. We can figure out what the energies are of different versions of the molecule, different isomers. And we can start predicting the spectra, which are really our first way of directly comparing the calculations to the experiment. We can sometimes get exact or accurate molecular geometries from X-ray crystallography, sometimes from NMR, but more often the easy experimental data to get is the spectrum of a molecule. What we then do often is extend the calculations to predict where the electrons are for particular electrons that are involved in the spectra that we're studying or in the chemistry that we're studying. And this is in the limit of what we call the molecular orbital approximation, which lets us treat electrons as though certain pairs of electrons are in certain spatial distributions. And we'll see a little bit of that in the talk. There's a number of things that are challenging. Very often what we're looking at are dynamics that depend on energy differences between systems. And the energy difference has to be really accurately calculated in order for us to get precise comparison between quantitative comparison between experiment and calculation. And you'll see that we're kind of pushing what we're really able to get away with in some of these calculations. We have trouble getting really good models of solvation. Solvation is when we have our molecule surrounded by a bunch of other molecules, and sometimes there's strong interactions that are hard to calculate accurately, given the fact that solvation is also an extremely dynamic process. And the calculations we're doing are based really on this rigid picture of the molecule, the nuclei not moving while we're solving the electron distribution. In some other experiments, not the ones I'm going to be describing, we're trying to model fluorescence intensities, and that's really problematic. But the other thing is that in general, large molecules are hard for us because the resources that we're going to need to invest in the calculation increase roughly as the number of electrons to the 2.5 power. And that's true for these density functional calculations I'll be describing. For more accurate methods, the power law, not surprisingly, is quite a bit worse. We use a number of programs, but almost everything I'm going to tell you about today was calculated using Gaussian, which is general purpose program found in many, many departments. Really nice graphical user interface, very user-friendly as these kinds of things go, still pretty powerful and flexible. But when we have to do much more accurate calculations, when we're looking for energy accuracy of the order of a couple of kilojoules per mole, then we need more demanding methods where Gaussian is not so great. And then we have some other programs that'll help us out with that. A quick survey of methods that we can use for these electronic structure calculations. Molecular mechanics, I shouldn't really call an electronic structure method, but the goal is the same. It's generally to predict properties and relative energies of systems. Molecular mechanics is classical mechanics applied to chemical systems, and it's based on classical force laws where the parameters describing the magnitude of the forces and the dependencies on distances between atoms and so on are obtained often by quantum mechanics calculations and then just plugged into a lookup table so that from that point on the calculation can be carried out as a completely classical calculation. Semi-empirical methods attempt to take things closer to the real quantum mechanics, essentially solving the easy part of the Schrödinger equation exactly, and then using empirical solutions to the hard part. They're extremely fast, and when they work, they're surprisingly accurate. And more than once, I've spent several days on a really demanding calculation only to find that I could have gotten the same answer in about 5 minutes with one of these semi-empirical methods. But when they fail really badly. And so it's one of those cases, as with a lot of empirical approaches, you just don't know whether you're getting a good answer or not until you use a more demanding method. Density functional, this is where more than 90% of computational chemistry, or at least computational quantum chemistry work is being published today. DFT theory was developed, or DFT was developed for solid state systems. And was found to operate extremely efficiently and with a relatively high degree of accuracy for small molecules as well. The DFT method is based on, instead of trying to solve the Schrodinger equation, coming up with an empirical solution for the relationship between the electron density, rather than the wave function, the electron density and the energy of the system, the electronic energy. And it's another case where much of the problem can be solved theoretically, and we have accurate solutions for a big part of the problem. But then there are two key parts of the problem, the exchange and the correlation interactions among the electrons, where we just don't know what the formula is that relates the energy to the electron density. And that's where the empirical part of the solution comes into play. So many methods have been developed using adjustable parameters that have been trained on large data sets. And the B3-LIP method will account for almost everything that I tell you about today, developed now almost 35 years ago, and still probably the best kind of cost to benefit ratio of any of the DFT methods. One of the fastest methods and surprisingly accurate. And then for some of the other cases that we're interested in, we do ab initio calculations, which try to solve the real quantum mechanical problem within the limits of certain approximations. Just to give you a rough idea how these stack up against each other, here in the middle, I've shown just a few sample parameters calculated using DFT methods, more or less the way that we would normally run them. You can see for bond length, we get a pretty good number. This is the electron affinity for a negative ion going from CCH to CCH minus. That's normally a hard number to calculate well, and you can see we can get some pretty serious errors with methods that we might expect to be pretty reliable. But in fact, with B3-LIP, if we use a reasonably large basis set, we can get pretty good numbers. We can get really pretty good numbers for a bond association energy, having acetylene drop off a hydrogen, how much energy has to go in. The DFT method is off by about 10 kilojoules per mole, or about 2 kcals per mole. And we get marginally accurate vibrational frequencies for predicting spectra. This is actually kind of unfair because this is a really hard vibrational constant to calculate well. This is the CCH radical, and the fact that it's a molecule with an unpaired electron already makes the calculation a little more complicated. You can see how horrible some of the other methods are that we throw at this problem. And DFT is actually not doing too bad in comparison. Just to show off, we can use these more highfalutin ab initio methods and get better numbers. In particular, we can get really quite accurate electron affinity, can get a bond association energy within about 3 kilojoules per mole. So a factor of 4 or 5 higher accuracy in terms of relative energies. But it comes at great cost. To do these ab initio calculations, we're spending about 10 times the resources that we're spending for the comparable DFT calculations. So all of the work I'm talking about today is work that we're doing in collaboration with experimentalists. And first of all, I wanted to tell you about work that we're doing with Hani Omori. He's a transition metal organometallic chemist at the Sorbonne in Paris. And he's particularly interested in making kind of novel complexes, sometimes with two different transition metals involved. Sometimes he's making cages and trying to see what their properties are with respect to trapping and transporting other compounds. So we'll take a look at a couple of examples that touch on each of those cases, beginning with this molecule called a dithiolene. So Hani is using this molecule on the left, It's a complex with iridium as the transition metal. This group on the bottom is a cyclopentadienyl molecule with methyl groups. We call it CP star. And he's using this to stabilize systems that otherwise are normally really reactive. And he's ending up with these bimetallic complexes with the original iridium and then a metal here, which can be either rhodium or iridium. And he's looking for interesting properties with respect to the electron transfer within the compound, hoping that these two different metals and the fact that we have some conjugation, we have kind of like a small electron transport system available through the ring here. He's looking to see if he can get interesting electron transfer properties. And this then can be applied to molecular electronics or to new optical materials. He's characterized the structure using X-ray. He's got UV vis spectra, which will tell us about the electronic states of the molecule, particularly relevant when you're trying to look for electro-optical properties. And he's also measured some electrochemistry. Our job was to figure out what the orbitals were, where the electron is that's responsible for the brightest UV vis transition, the transition associated with the primary electronic change in electronic state in the molecule. And what we're looking at here is the experimental UV vis spectra obtained for absorption in 4 complexes related to this experiment. So there's this initial complex, which is not shown, 2, which is the smaller iridium complex, the starting material, and then structures 3 and 4, which are these larger bimetallic complexes with either the iridium or the rhodium as the second metal. And so we get a number of spectra, and these are electronic spectra showing up in the visible and near ultraviolet range of the spectrum. So here are wavelengths in nanometers. And as we go to the left in this graph, what we're seeing are excitations from the lowest energy electronic state of the molecule into increasingly high energy excited electronic states. And wherever you see a peak, there's light being absorbed because of the transition from a lower energy state to a higher energy state. To reproduce or to try to predict those spectra in our calculations, we run what are called time-dependent DFT calculations. DFT calculations inherently do not allow calculation of excited electronic states. There are variational calculations by default, which means that if we start off with a particular distribution of electrons, the first thing we do is tell the calculation to find the lowest energy state for that arrangement of the nuclei, which means that any electrons that were high energy converge to whatever their lowest energy distribution would be. With the time-dependent DFT method, you're able to mix in contributions from what would ordinarily be considered excited molecular orbital configurations and start predicting properties of the excited states. And that allows us to predict the UV vis spectrum of the molecule. So there's a bunch more spectra, but this time they're calculated. And what we're able to do then is compare these calculated and observed spectra, so the experimental spectrum on the left, the calculated on the right. And what I'd like to convince you of is that we have actually very good qualitative agreement between these spectra. In particular, the strong peaks show up in about the right place. The strong peaks have about the right intensity. We are able to predict both the wavelengths and the intensities of each transition. And because we get relatively good qualitative agreement, we think that we're able then to correlate the principal transitions in the spectra to the actual locations of the electrons involved in the transition on the molecule. I should point out that the reason the agreement is so poor at short wavelength is because when we run these calculations, we have to estimate how many electronic states we're going to need to calculate to reproduce the spectrum. And on the right, these spectra were all obtained by calculating up to 30 excited electronic states for each of the 4 systems. And that means that by the time we've gotten to the 30th state, we're seeing transitions that are at wavelengths as short as about 250 nanometers. In order to reproduce what's going on at 200 nanometers on the left, we would have had to go to 50 or 60 excited states. So now what we're looking at here are for molecule 2, this smaller iridium complex, and then the bimetallic complexes 3 and 4, 3 with the rhodium and 4 with the second iridium. These are the molecular orbitals that, for the most part, are responsible for those transitions. The HOMO -1 means the highest occupied molecular orbital -1. So this is not actually the highest energy molecular orbital, but the next one down. And very often, the strongest transitions, the ones that we can see most easily, are not the ones that correspond to the HOMO LUMO, the highest occupied going to the lowest unoccupied, but are nearby. And so in this case, it turns out that it's not the highest energy molecular orbital, but the next one down that's responsible for the origin of the electrons that are in these strong transitions. The thing I want to point out is that in all 3 cases, the strongest transitions correspond to orbitals that are initially localized on the sulfurs. And so therefore they're on the ligands attached to the metals. And then the upper state of the transition, so we're going to the LUMO, the lowest unoccupied orbital, the upper states all correspond to electron density on the metals, and with varying degrees of localization, either on the rhodium in this case, or spread almost equally between the 2 iridiums here. We're still going from a ligand to the metal, and so this is what we would call ligand metal charge transfer transitions, or LMCT transitions. And this is the kind of thing that Hani is looking for. He wants to see that these transitions do correspond to significant relocation of the electron within the molecule. And that's a good indication that this is a candidate for a new electronic or optoelectronic material. I also wanted to point out that this is a case where we had to be careful about solvent effects. Hani was curious about the reaction that actually formed molecule 2 here from a starting material, where instead of this dithiolene on the top, this ring on the top, the iridium was covered with acetone, solvent molecules. And he was a little bit surprised that he was able to displace those acetone molecules to get this complex to form. In other cases, that doesn't work. And so we carried out the calculation to estimate, well, here's the energy of the structure with the dithiolene, here's the energy with the acetones, see which one is lower energy. And we clearly got the wrong answer. We got that the free energy, G, would increase if we tried to form molecule number 2 over here from the starting material. And it was a simple case of not taking the solvation into account. What we had to include in the calculations in order to get at least the right trend in the behavior of the reaction was the fact that this molecule is not in the gas phase, it's surrounded by acetone. And when the acetones are liberated from the initial structure, they go into a bath of other acetones, which then stabilize those molecules very effectively. And as a result, between including a kind of nominal solvation model and then applying a more sophisticated method called Cosmo-RS, which takes into account more of the dynamics of the solution, we found that we could predict a delta G that was negative. And of reasonable magnitude, so that we were in fact getting, at that point, qualitative agreement with the experimental behavior. I should point out that this is one of the great dangers of computational chemistry. There's so many knobs to play with that it's very easy, as I try to warn my students, to carry out the calculation. If you have the right answer in front of you, carry out the calculation again and again and again until you get the right answer, and then stop, which is not really the way we want to be approaching the problem. Now, Honey's, as I mentioned, also calculates, or rather synthesizes these cages. And this was one of the scariest systems that he gave me to calculate. This is a nano cage that's based on 2 palladium molecules at the top and on the bottom, with bars to the cage that are formed out of these extended organic compounds. And you can't quite see it, but there are actually 4 of these strands coming down, 2 on each side. And he found that he could use these cages to host these platinum complexes in the middle. Now, the structures that I'm showing you here are obtained from the X-ray. And what was interesting to him, I'm sorry, I should go back, was that he found that the guest molecules, these platinum complexes, occupied one of 2 orientations within the cage. And so our job in this case was to try to figure out what the mechanism was for these 2 different binding arrangements. The main thing I want to point out is we were able to put this molecule together. I'm sorry, this is kind of a hazy picture. I was originally looking at it when it was too small. But all I want to point out is we were able to put together the structure and then calculate, for example, that the binding in the middle of the molecule, when the guest is in the middle of the cage, apparently comes from the oxygens on the complex being able to donate efficiently into empty orbitals on the 2 palladiums. And so this is kind of a classic sort of back bonding mechanism. And we're able to show here the acceptor orbital on the palladium and the donor orbital on the oxygen. But the thing that I found actually more impressive was that the large scale structure of the molecule, so this now is looking down along the axis of those 2 palladium atoms, the large scale structure was actually very accurately predicted by these calculations. We were kind of struggling with these because it's such a big molecule. We're not using as large a basis set as I would have liked. But we are still able to observe the right kind of oscillation or bending in the structure of these extended organic components of the framework. And in fact, when we looked more carefully, we saw that going all the way across the cage from one end to the other, for example, between the 2 palladium atoms, we were able to predict the distance separating them to a value that was in good agreement with the X-ray structure within 1/10 of an angstrom. And the dihedrals for this kind of gentle sort of wave in the organic framework, we were able to predict to within 10 degrees, which is better than I would have expected. Okay, I want to tell you next about some calculations that we've been doing in collaboration with Doug Grochon in our department now. Doug is also a transition metal organometallic chemist. And his interest, though, is in applying these molecules to catalysis. So he makes catalysts that either accelerate reactions that are useful for fine chemical synthesis if you're trying to make really specific compounds. He's also looking at applying the catalysts that he makes to the problem of water reduction. So going from water to H2 and O2. And I'm going to focus on the work that we've done in collaboration with him on what he's called his zipper catalyst. This is a molecule that helps an alkene, so a carbon chain with a double bond, move that double bond from one site to another in the molecule. And it's following the thermodynamics, which tell us that if the double bond is at the end, you can actually make So they generated another molecule. This time you can see we're going from this CP ring, that's the cyclopentadienyl again, to a CP star, again with the 5 methyl groups around the outside. And sure enough, that did help isolate the 2 alkenes. So if you wanted that, you could pull it out. The problem was that the reaction at that point was actually very slow. And so instead of using that, they changed the nature of the connection between the ruthenium and another part of the molecule with a nitrogen atom to get this, this catalyst. And you can see actually the main change is that we've taken away this molecule, an acetonitrile, to allow the nitrogen in this ring to bond directly to the metal. And this now gives, again, an opportunity to isolate the very first reaction product that's formed before the reaction continues on, but at a speed that's not quite as fast, but still comparable to what was obtained for catalyst number 1 here. This is a great catalyst, among other things, because it's able to work effectively with a large variety of substrates. So here are molecules I'm talking about with double bonds at the terminal end of a carbon chain. And the Grochon group was looking at how this catalysis might be affected by allowing the substrate to branch at some point, by putting functional groups at one end of the molecule, so that now the as the double bond moves, it's not necessarily moving to the middle, it might be moving all the way towards the opposite end. Now, there are, as always in experiments, issues that come up if you try to go exploring too far. So for example, this alcohol group in pentanol deactivated the catalyst, the reaction would stop. They had tried, it was because the pentanol didn't work so well that they went to this pentanol silyl ether, instead of having a hydrogen, having this Si and then T-butyl group at the end. And they were able to get the reaction to go in that case. Overall, what we're trying to do here is take the kinetics that they've measured. So what they're doing is monitoring the reaction by taking an NMR spectrum of the reaction mixture sometimes every 10 minutes, sometimes every couple of minutes, sometimes every half hour, and following the progress of the reaction that way. Now, I'm going to describe initially some much more mundane computational chemistry, because what we're interested in doing here is fitting the data that they get to curves that depend on the values of reaction rate constants. And so this is a relatively straightforward problem in fitting a differential equation to, fitting parameters in a differential equation to experimental data. The rate laws for kinetics are first order differential equations. You get a relatively large set of coupled first order differential equations, and then all that we're doing is integrating them and solving them. But I did want to mention first that there's a number of things that kind of complicate the analysis here. In a lot of chemistry, we're used to the idea that we can just fit a reactant or product concentration curve like the ones I was just showing you. apologize. What we're looking at here are concentrations of reactant and product as a function of time based on the NMR spectrum. So what we're used to is the idea that we could just take that and fit it to a function, an analytic functional form like e to the minus kt or 1 minus e to the minus kt. But here we have, in particular, an equilibrium that's established. At long times, the reactant concentrations don't go to zero because, in fact, the reactants are stable. Intermediates that are formed along the way are stable to varying degrees. And so we end up with a variety of concentrations that are all non-zero. And that means that there are reverse reactions that are also important in the analysis. And that's what's necessary to set up some kind of equilibrium. Reverse rates actually complicate things significantly because we usually don't resolve them since the net reaction is really moving forward. We don't resolve the effects of the reverse reaction steps so well, and so they tend to be more strongly correlated than the forward steps. There's also some ambiguity in how we deal with the catalyst. We can treat the catalyst as though it's simply out there in the environment. It's not directly a reactant or a product. However, depending on what we're able to measure and depending on the residence time of the substrate on the catalyst, it may be important to model the reaction as though it's bimolecular, as though you actually have reactant hits catalyst, and then you form a complex, and then the complex comes apart, rather than just the reactant turns into the product in the presence of this other thing. We have trouble with concentrations at early times because these reactions are often relatively fast and things don't mix at the same time. There can be some difficulty getting the temperature to settle down. On the other hand, we need those data points at early times because if that's where the reaction is happening fastest, that's where our best information is about the reaction rate. And finally, the concentrations in many cases get so low that we're comparing concentrations at the same time that may be different by factors of 100 or more. And therefore, we have to use a little bit more complicated analysis than we might be able to do if we were, say, just trying to use Solver in Excel. So we have a code that we wrote ourselves, not very complicated. Again, we're solving these coupled first-order differential equations by fitting rate constants to them. And sometimes we may also have to vary the initial concentrations. That's not necessary so much in this work where the initial concentrations are well characterized. However, the start time again can be ambiguous. And so we have, in many of these fits, varied the effective initiation point of the reaction. All we're doing is Runge-Kutta of fourth order integration and least squares optimization routines that we got out of the venerable numerical recipes book by Press. So here what I'm doing in a series of slides, I'm going to run through these pretty quickly, but I just want to point out what we're doing on the left is showing the kinetics of the catalyst number 1, and on the right, the improved catalyst number 2, or actually it was number 3, if you're trying to isolate in particular the first product that forms. And so here what we're showing is the initial 1-alkene concentration decreasing, the 2-alkene concentration growing in, and over a longer period of time, the 3-alkene concentration. So that's going from 1-hexene to 2-hexene to 3-hexene. And we're just kind of writing that in shorthand here, 1-hexene to 2-hexene to 3-hexene. E is a particular arrangement of the molecule around the double bond that becomes an issue once you move the double bond towards the middle of the molecule. And what I'm indicating here is that we are modeling both the forward reaction steps with rate constants K1 and K2, and the reverse reaction steps K-1, K-2. Here, the same thing for CP star, and you can just see qualitatively, we're looking at the same time interval here. If you were only interested in getting the 2-alkene and didn't want the 3-alkene, there's actually a nice long region of time in here. Notice this is logarithmic scale along the horizontal axis. There's a long period of time here where you could actually extract the product, quench the catalyst, and you would have almost entirely the 2-alkene rather than the a mixture of the 2 and the 3, or a mixture of the 2 and the 1. So this is the kind of thing that the Grotjahn group was trying to get at. And part of our job with this analysis was just quantifying the degree of isolation, how selective is the catalyst for the 2-alkene. Here's a case where we had to throw away some data points at early times because they were clearly not lining up with expected trends based on the rest of the data. And there is a difference in the amount of catalyst present in order to get these timescales similar. So I said the CP star catalyst is comparable in rate to the CP catalyst, but it is slower. And because of that, we're actually looking at any given time at 3 times the concentration of catalyst. Okay, so that's basically what's going on. I just want to point out that as we looked at a number of these substrates, here's the octene, same kind of trend. Once again, you can do a much better job of isolating the 2-alkene if you're using the CP star catalyst than the CP catalyst. But now we're starting to see, as things get more complicated, other things that we need to throw into the rate analysis. In particular here, not only is the E isomer forming, but the Z isomer, which is the difference between what we would normally call trans and cis distribution around the double bond. And in this reaction, we're able to see some of the Z isomer forming. And of course, we have to put that in if we're going to model the kinetics accurately. Let's see, this is the decene-ol, and one of the complications that's coming up here is this is now a really long alkene. And as the reaction progresses, we actually get to alkenes that are so similar that the NMR data is not actually able to identify them. We can't necessarily tell the difference between E and Z. They could both be present at the same time, and so on. And so in the analysis, we have to say, well, we formed this 6 decene-ol, and then we go to other stuff after that. The interesting thing for us was that the 6 decene-ol itself is already not identified in the spectra. You can see it's not listed here, but we have to model not only the formation of that molecule, but how it then goes on to form other molecules, because this downward trend that you see in the 8 and the 7 decene-ols here is because the 6 decene-ol is continuing to be catalyzed to form other things and sucking more concentration away from the 7 and the 8. As we go on to even more complicated systems, it turns out we have to include some bimolecular steps because we have cases where the catalyst complex has a relatively long lifetime. And in this case with the hexenone, we're finding that yet again. And this was one case where the 2-alkene was actually not that well isolated in the CP star catalyst. But for all of the other substrates that were studied, the CP star catalyst did a much better job of isolating the 2-alkene from the other possible products. So we're going to get back to the computational quantum chemistry, but first of all, let me just show you, these are the results we obtained using the rate constants that we were able to fit for the Grotjahn group data, showing the ratio of the rate constant to form, so K1 is the rate constant for forming the 2-alkene, K2 is the rate constant for forming the 3, and we're looking for a high ratio here so that we form the 2-alkene quickly and the 3-alkene then relatively slowly. So the bigger this ratio is, the easier time we're going to have isolating the 2-alkene. And this just shows that sure enough, for all cases except the hexenone, the ratio was much greater for the CP star catalyst than for the CP catalyst. Now, based on a previous study that was carried out primarily by Thomas Cow in Grosjean's group, we have a pretty good understanding of what the mechanism is for the zipper catalyst. And so a student of mine, Ryan Sindewald, has been trying to find out how that mechanism, if we apply it to these reactions, how well it predicts the trends that were observed in these experiments. So here again are the experimental ratios of K1 to K2, and here now are the calculated ratios that that Ryan was able to come up with. I should say these are ratios that were obtained initially with kind of our default methodology. And then when we tried to improve the methodology, the agreement actually got a little bit worse. And that's important for the next directions we're going to take. But I did want to point out that to the extent we're looking at the right rate determining step in this reaction, we are able to predict qualitatively the correct trend that the 2-alkene forms quickly, the 3-alkene forms more slowly. And in fact, if we can go another step, going from the, let's see, in this case, going from the 3-alkene to the 4-alkene, things slow down again. So we're able to predict those things qualitatively, but you can see numerically the agreement is not very good at all. And in particular, the 5-methylhexene. And this was a clue that we're probably not looking at quite the right rate determining step. I should also mention the ratio between the rate constants is really not the smartest thing to compare. What we should be looking at is the energies, because we understand much better what the expected errors are in the energies. To calculate these rate constant ratios, we're actually taking the exponential, we're taking e to the minus delta e. So the difference in energies and then putting that in the exponential. These K1 over K2 ratios that the Grosjean group is observing correspond to energy differences of 2 to 4 kcals per mole, where we expect the error in the DFT methods to be about 2 kcals per mole. And so we are pretty close to where we're really testing the limits of the accuracy of these methods, except that for something like 5-methylhexene, we should be able to get that. And the fact that we were predicting a smaller K1 to K2 ratio here than for the other substrates was a pretty good indication that something was wrong. And Ryan's been pursuing this. It looks like for these cases, the rate determining step may actually be earlier in the mechanism than what it was for the butene case that Thomas Cow was studying. And so he's now looking at those rate determining steps, rather at those activation barriers. And preliminary results are that, in fact, that's going to help explain why, in particular, the 5-methylhexene has such a good ratio here in comparison to these other molecules. So we think that the numbers will get better, but it's already with a lower level of theory and with the rate determining step that was important in the butene substrate, we're getting good qualitative agreement with the experiment. Okay, let's see, I'm going to skip over this. This is just pointing out the magnitude of the concentration differences that we have to work with. And I also wanted to point out that from our analysis, we're able to show, in some cases, pretty good agreement with thermodynamic constants that are available in the NIST database. And we think that we're actually getting better precision, although it should be emphasized that this is for a particular environment. This is with an acetone solvent, and that's not necessarily the case for the studies that are being quantified in the NIST database. Okay, I did want to finish up with one quick review of some work that we did about this time last year, collaborating again with one of my colleagues in the chemistry department, Jinggu, who's a brilliant materials chemist working over in EIS, and her interests are in artificial photosynthesis, in particular converting CO2 back to a fixed carbon, and also looking at how energy and electrons are transferred in photocells. So this was a system, I'll show you chemical structure in a little bit, but she's working with a MOF. This is a big thing. These are metal organic frameworks. So again, metal, although in this case not transition metal, because we're putting in the middle of these organic systems a zinc atom. And then what Jingu is doing is, they call it infiltrating the compound with oxygen. And, oh, excuse me, they're infiltrating the MOF with zinc, and then they're dumping oxygen into it. And as the oxygen goes in, they see changes in the reaction that's taking place. What they're looking at is the electrochemical indications of the progress from carbon dioxide to carbon monoxide. And so now the degree of infiltration with oxygen is causing a shift in this UV-Vis spectrum. And it's kind of a subtle shift. There's a small decrease in intensity. We're going from the pure metal organic framework to the metal organic framework with the zinc present. So that accounts for a jump of about 10 nanometers in the lambda max, the peak position of the spectrum. And then what's going on is they're providing more and more oxygen as we go up in this graph. And as that happens, we get a further shift of about 5 more nanometers in the lambda max. And again, this decrease in the absorbance intensity. So Jingu is not able to get direct structural information about this system because it's too soft to get an X-ray. However, she's postulating that as the oxygens go in, the zinc is being pulled out of the metal organic framework, out of the structure, and that's inducing strain, which is responsible for the shift in the spectrum. So the question was, can we actually predict this trend? And so once again, we're going to be using time-dependent DFT methods, and the results I'm showing here are the initial spectrum. So this is the predicted UV-Vis absorption spectrum when the zinc is right in the middle of the plane of this metal organic framework. And then as we move the zinc out, so we're just forcing the zinc to be deformed from the center of this plane, we see the same trend as Jingu sees. We see a mild shift to higher wavelength and a mild decrease in the intensity of the transition. And so this is actually what we're looking at. These are porphyrin rings with these 4 nitrogens, the blue atoms, in the center, roughly in a plane, and then this light blue atom is the zinc. And the zinc is being coordinated to oxygen as represented by this water molecule at the top. So we're going from 0 to ½ an angstrom to 1 angstrom of deformation of the zinc out of that plane. And that appears to be responsible for the shift in the spectrum. And so this is a case where we're not proving what's causing this shift. We're merely showing that we have a model that is consistent with the observed experiment. Okay, and that's everything I wanted to give you. I do want to thank, of course, all my collaborators and the people who worked with them. In particular, Eric Paulson obtained most of that time-dependent NMR data that I was using for the kinetics analysis in Grotjean's molecule. Thomas Cowgan ran the calculations to determine the original mechanism. This is Jingu's group working on the metal organic framework. My group, I have a couple of pictures I can show people. So Ryan carried out those calculations on the other substrates for the zipper catalyst and is continuing to work on that. Sasha is working on a couple of projects, including one with Carl Carano, also in our department. Harry is also working on a couple of collaborations and has worked on one of the collaborations with Hani Amori, as has Ryan. And Sally Bachori is working on another collaboration with Byron Peirce in our department. So I want to thank all of them and thank all of you for your kind attention, and ask if there are any questions that I can help address.
The floor is open for questions.
I'm sorry, I meant to leave you more time so you could get out and enjoy the beautiful sunshine and 98-degree weather.
I guess it was too clear.
It was. I have practiced this talk too much. Well, thank you all very much. I really appreciate being able to present this work to you.
Any questions, comments, complaints, compliments? Well, in that case, if
Nice talk.
it was a very, very enjoyable talk, so thank you everybody for attending and have a wonderful weekend.
All right, thank you. That's high praise, Peter. I appreciate it.
Bye-bye.
Bye-bye.